say thank to both Katie, Simone, and the organizer for this very beautiful conference. I really enjoyed it, and I'm also very happy and grateful to talk here today. All right, so I will present a work in collaboration with my PhD advisor, Jan Mas, and Eva and Peter are two people in Bonn as well. So I will talk about discrete-to-continuum limits of dynamical optimal transport. And I can show you actually here what is the outline of the talk. So I will introduce, let's say, the general setting in the continuous problems. And then I will move to the discrete setting. So discuss about how to make this continuous problem into the discrete one. And then I will discuss precisely the discrete-to-continuum limit in the setting of periodic graphs. And during the talk and at the end, like a bit in between, I will just try to give you some examples and possible applications of this result. All right, so about the setting at the continuous level, I think we have seen enough time Wasserstein-2 distances during this workshop and dynamical formulation. So I just put one slide just to recall that as a starting point is the dynamical perspective of optimal transport. Which in the specific case of Wasserstein-2 really means to minimize the total kinetic energy between all the possible solution of the continuity equation, so all the possible evolution of the mass. So of course, this is just the case of Wasserstein-2. What I'm interested in is essentially the same type of problems, but a bit more generally. So where instead of looking at the kinetic energy in this part here, I'm interested in a bit more general setting where I just consider a given convex function. All right, so in this case, f is just some convex lower semi-continuous function of the mass and the momentum. So I also did this chain of parabola. I would always work with mass and momentum to make the problem convex. And aside that is essentially the same problem as before, but the function f can just model different situations. So let me just give you some examples. So again, the quadratic choice with respect to the flux variable is the one corresponding to Wasserstein-2. But of course, you can consider also more general situations, especially for Wasserstein-P, of course. You can always consider P homogeneous cases, but you can also include in your model some non-linearity dependence on the mass. We actually have seen this exactly in the talk of Emanuela this morning. This can allow to consider in the model some crowd effect. That, for example, could be that the velocity of my motion is not really independent on the other particles. But if I have more particles, for example, I can have a slow down velocity in the motion, and this can be modeled by this non-linear dependence on the mass here. So of course, it's of the same type with the different choice of the function f. And then also one, let's say, I think more, say, easier setting is the one of the things I would call the flow-based problems, where the cost depend only on the flux variable. So in that case, actually, the picture is easier because we don't have any dependence on the mass in the problem. So actually, this dynamical formulation can be also reduced every time to a static formulation, because in fact, you can see just by Jensen's inequality that the cheapest choice of the flux is to just be constant in time. All right, so because of the convexity of the function, so the average in time will always be the optimizers in the problem. So in fact, I can integrate in time this equation and get this static formulation here in sort of like Bregman type of divergence. And this includes, for example, Wasserstein-1, but also like negative Sobolev distances and different problems. All right, so the motivations about working on this general setting is of course, I said, optimal transport, and also the study of other type of evolution like traffic flows, congested transport, and so on. And we've seen during this conference many times that there is a nice connection between gradient flows and optimal transport, and this was actually possible through this dynamical interpretation of the distance. I'm not sure about it. I think nobody actually said something about another connection with another part of mathematics during this conference, which is this connection with some Riemannian geometrical properties of the manifolds. So when you are working on a manifold, there is a very nice connections between, for example, positive curvature condition on the manifold with respect to some properties of, for example, the entropy along the geodesics of Wasserstein-2. So this will not be the focus of my talk. What I want to say here is that there are some very nice connections, which is not only modeling of the problem, which somehow was possible only through this dynamical interpretation. And so what actually happened in 2011 when Mielke and Mas worked on the discrete optimal transport was exactly to try to generalize not only the definition of the transport, but also to try to recover the same type of structure we have at the continuous level. So gradient flows, Ricci curvature, and so on. All right, so let me introduce you to the discrete optimal transport, and now we start with the quadratic case, so the original work of Jan and Mielke. So what is the setting for me when I say discrete? So we should just always keep in mind it's going to be like a weighted graph. So X is just a set of vertices, E are those green connections, so the edges, and omega is a weight on the graph. Probably something that Antonio and Deia would have called eta in some days ago. All right, and once we have this discrete setting, what we want to do is to define a discrete distance over the graph. And intuitively, you just simply do it by taking the dynamical formulation and discretizing in some suitable way. And actually, we've seen already this formulation, I think, in the talk of Antonio and Dejan. The natural way to do it is to take a discrete continuity equation, where instead of the continuous divergence, we have a discrete divergence. Here, I'm not assuming any skew symmetry on the flux, so I'm just writing this difference here. And then the action will be defined in some sort of natural discretization of the continuous one, where we have this kind of strange situation where we need to take an average of the density because we don't really have a density defined over the edges, so we need to choose this function theta. And already advertised in previous talk, the choice that they made in these papers, what the logarithmic mean, that somehow was the right choice to recover all the continuous theory also in the discrete space. So in particular, what they do is they choose this specific choice of the average, which is probably not the first one would have in mind. And in this way, they get the same structure. So if we take the gradient flow of the discrete entropy, we end up with this so-called graph fit flow. So the graph fit flow is just when you take the discrete Laplacian, where the Laplacian is just obtained in the following way. You can see in many also probabilistic perspective, it's just a Markov process, continuous macro process, where the rates of jumping is given exactly by these guys there. All right, so what I want to do is to discuss about some discrete-to-continuum approximation results. Actually, this is part of two papers. The first one was a one-dimensional result, where we first tried to understand what the general situation was, and then we found out that although with very different techniques, the result was way more general, and then we actually managed to do this in a bit more quite more general situation in high dimension and for any energy. And actually this literally appeared today, so I'm very happy because I was running, trying to make this happening before the conference. It really happened a few hours ago, so that's pretty nice. All right, so before describing the exact setup, let me just make some literature. So what is discrete-to-continuum? So what was the first result in this setting? So the first one that I'm aware of is the work of Gilly and Mas in 2013. So they proved that if you take the continuous torus in every dimension and you take the easiest discretization you can have in mind, when you just take the grid, so you just take the square with the, and you just discretize with this squares of size 1/n, then you can just define a graph structure very intuitively by taking the center of the cubes and nearest neighbors interactions, top of connections. And then you can consider the corresponding distance. And what they proved is that the discrete distance converges to the continuous one when you take n goes to plus infinity. So when the graph is getting denser and denser. This was the first result, deterministic, so no randomness, just specific type of partitions. And then Nicholas, I think actually this is the year of publication, but I think he proved this even, I think 2017, 18. He provided another approximation result, discrete-to-continuum, but in a random setting. So where instead of taking a precise deterministic partition, you just throw IED points on the torus, and then you define an edge between the points if the points are close enough together. It's a very beautiful result. The setup is very different, not only because it's random, but because of this diverging degree situation. So actually the points are seeing a lot of neighbors that goes to plus infinity when n goes to plus infinity, which is very different from this setup where you only have 2D neighbors in some sense. So after this works, essentially the point was, all right, we have these approximation results. The problem is especially the first example is very structured. So it's very symmetric. And the question could be, can we do something more than just the simple grid? And what they actually proved in last year, 3 years ago, actually, that it is not always true that the distance converges to the continuous one. So if you take finite volume partitions, essentially means you take a convex body and you take just partitions in convex cells. There is a natural graph structure you can associate to this, again, by taking nearest neighbor sort of interaction. And they show that the convergence is only true if you assume an additional geometric assumption, which they called isotropic condition. I will not write here or discuss here this condition, but at the end of the talk, I promise I will go back to this setting. I will show you what does it mean in the periodic setting where things are a bit easier to write it down. But there are situations like this where you have the convergence, and in my opinion, very stable situation, like very easy picture like this where you don't have convergence. So this was essentially the starting point of my PhD. And we were trying to understand whether we can do something more. So, okay, we have a situation where the convergence appears. We have a situation where we don't have convergence. So what happens when you don't have convergence to Vasten 2? So the setting I want to describe is the periodic setting, where we managed to give a full answer to this question. So what do I mean with periodic graph? I mean the following. We are, for simplicity, let's say we are in RD, embedded in RD, and I just have a graph which is locally finite. So in each cube, I only see this finite number of points. You see these blue dots, and also the finite number of edges. These green arrows here are the one inside the cube. And then if you just shift the graph, you get the same picture, which means that essentially all the information of the graph is in this side, this cube, and all the edges pointing out from this cube. So what I want to do is to study the problem I told you before, but in a discrete setting, which means I don't really make a choice of the function f. I just take some convex and local function f. Local, because I mean, it could depend on the whole graph, but I want I am focusing in this problem, which is a bit different from some previous talks, into some local problems. So I really want the dependence only to be, for simplicity, let's say inside the cube. But the important thing is just that it's locally depending around the cube. And then I just minimize the action in the same way, where I have the discrete continuity equation and not the continuous one. And maybe to fit also with the previous talks of a few days ago, if you assume JT to be skew symmetric, you get the same old divergence, which is okay because all the optimizers are actually skew symmetric, so nothing changed. All right, so what I want to do is to study this class of problems, and let me give you again a few examples. So the example you might have in mind, a simple one, is energies of this type, which I would call the edge-based case, where you only have a sum of some energies fxy, and then you just sum over all the edges inside the cube, inside the green cube. And if you choose special type of energies like this one, the quadratic choices, you get exactly this mass-Mielke type of discretization of the graph. Here I even brought this concave dependence here, because if you want to approximate this generalized Vasten distance, we can do the same. We just need to plug in a discrete setting. And exactly like before, the flow base means when you don't have a dependence on the mass. And again, you get the static formulation. Even in the discrete setting, instead of the continuous divergence, we have the discrete divergence. All right, so what do I want to do? I want to approximate to study the limit as the mesh gets finer and finer. So what I want to do is to take this graph and the problem, and I want to rescale it. So when I say rescale it, I think the following. So this red cube is the same one as in the left-hand side. I just zoomed in to see a bit easier. And if I rescale by a parameter epsilon the graph, I get a lot of copies of the same graph, but smaller inside the cube. So if I just multiply by this epsilon, the graph, I get a lot of copies of my graph inside the cube. And then what I want to do is I want to rescale the energy. And how do I want to define the rescaled energy? I want to say, well, I take the energy of each of these small cubes, and then I take an average of all these contributions. Of course, I also have to scale the mass and the flux if I want to see something local in the limit. And the nice scaling in this case, the right scaling is to divide the mass by epsilon to the power d, and to divide the flux by the epsilon d minus 1. Because in fact, the flux, you should think of the flux as a flux over a surface. So you should really rescale this by a surface type of term here. This means, this minus z, this means I'm centering the problem on this cube, and then I'm taking the average over all the cubes. It's just a natural rescaling of the problem if I have a denser graph when I rescale. And so what we can do in this situation, I want to study the limit as epsilon goes to 0. So when epsilon goes to 0, we can prove the following thing. So, and we can do this in high dimension, in any dimension, and for any f, essentially. I wrote here this superlinear growth condition. In fact, just for simplicity of the presentation, I think also Dayan last time said that when you don't have good growth condition, you might have problems of singular parts of the measure and things like this. So let's say in this case, we don't have this problem. And what we are able to prove is that as epsilon goes to 0, the discrete cost converges to a continuous one, which is exactly of the same type of the one I showed you at the beginning. So it's a minimization like a Benamou-Bernier type of formula, where the cost is given by this f home. So there are two layers of let's say, of results here. So one thing is that we have a limit. And the second thing is that not only we know that the limit is of this form, but we can say something way more specific about the limit f home. So we can compute essentially explicit the f home as a function of f, the one we started from at the discrete level, and the graph we had at the beginning. And I will show you some examples. So the d=1 case for the quadratic choice of the energies was the first contribution. It was very different. I mean, it was obtained with some techniques which are very typical of the quadratic case and of dimension 1. And in fact, in high dimension, we can do something more, not really so important at this level. We can really prove gamma convergence of the functional defined on the space of curves. So when you take optimal transport here, you're taking the minimal, this, let's say, kinetic energy between all the curves. In fact, what we can prove is really gamma convergence of the function defined on the space of curves. And then as a consequence, you get actually a convergence of this cost. Oh, all right. So I promise I have this formula for a form. So I would try to explain to you how to compute the limit. So let me just give some notation. So we have this original graph. So before any rescaling, and then I would just define the norm of m as the mass in the cube. So let's say the sum of the mass in these 3 points. And then here we see actually something we've seen, I think, in Dayan talk. So for every vector in RD, I define the effective flux, which is a discrete object. I mean, it's still in RD, but is somehow managing to pass from discrete to continuum. So J is the discrete vector flux. And then I just take the sum of the flux over all these green arrows, where Jxy is the flux and y minus x is just the direction of the edge. So this guy is somehow able to, for any discrete vector fields, to define a continuous J. They really should play the role of the continuous flux at the continuous level. And I will show you actually a precise example. And so if this notation is in the game, then we can really compute the form in the following way. So we fix any rho and psi. So rho is just a number and psi is a vector. And then I do the following thing. I take between all the possible mj on the cube, all the possible way to put the mass and the flux on the cube, I want to take the one that minimizes the discrete cost with some constraints. And the constraint is that the total mass has to be equal to rho, the first variable. The total flux has to be equal to psi. And the discrete divergence has to be equal to 0. So every time you give me an f and a graph, I can compute this guy for every rho and psi. And this will be really like the continuous energy density that defines the promise in the limit. So I don't know how much time I have. I think like
about 9 minutes.
Great. So I will maybe, I think it's constructive. For me, it was constructive to try to see at least one example about construction a competitor for this self formula. So suppose we fix in dimension 2, because, well, we only have dimension 2 available here, rho equal to phi and psi equal to 2, 3. So the first constraint says that I need to find a way to put the mass in these blue dots in such a way the total mass is 5. We can do this in a very easy way in many different ways. Let's say, for example, we say 3 here, 1 here, and 1 here. So this would be a competitor for the mass. And because this guy, at least for me at the beginning, was a bit mysterious, in fact, when you want to find a J here on the green arrows, such that the effective flux is equal to 2, 3, this really means that the horizontal flux from the cube outside, the horizontal one should be equal to 2, and the vertical one has to be equal to 3. I don't really care what happens here. You can actually prove it is invariant by shuffling the points inside because we have divergence 0. So the only thing that matters are what happens here and here. So an example would be the following. So you have these values on the arrows, for example. And if you see how much flux is going outside is this number 2, which is why, because we need to have this competitor here. And if you look at the vertical displacement outside, from inside to outside the cube, I have 4 going out and 1 getting in. So it's 4 minus 1, we get exactly these 3. It's not trivial to see, but whatever happens inside here is not really important because of this divergence 0 condition. So whenever you want to find a competitor, what you really need to do is just shuffle things inside and be sure that the flux at the boundary is the right one. All right, so I just want to conclude with some, let's say, the application we had in mind, actually the one we started from. There was this final volume situation. So what happens in that case is the following. So final volume, I mean exactly what I was saying at the beginning, but first I want to be periodic to try to apply our result, which means I just take a partition of the cube and I rescale it and then copy it again in the cube. This gives me like a random, a periodic graph. Just again, I just say that 2 cells are connected by an edge if they have a common interface. And then there is a particular choice of the weights, which I will not comment too much, is this geometric choice. It's very typical already in the numerical analysis community when they want to do final volume approximation of PDEs. This is the right choice of the weights for some scaling reason. And so in this particular case, so for this special type of energy, so the Vasten 2 type of cost, so we can really say something more. So of course, for one-dimensional, what we get in this case is the following. So the limit will be a multiple of Vasten 2. So remember, at the beginning, I told you if you're symmetric, you get Vasten 2. If you're not, you don't get Vasten 2. So what we can do here is to say, okay, we still get something which is explicit, and it's a multiple of Vasten 2, where the multiple is exactly given by this F home 1. It's always cheaper, but it can be strictly cheaper. So you don't always get Vasten 2. And in the multidimensional case, you get the following general result that says, okay, we still get something of this form, like in the general setting. But we can say something more, something somehow peculiar happens is that we always have a sort of Wasserstein 2 with respect to a norm, which I called here norm home, homogenized norm. But this norm does not need to be equal to the Euclidean one. So you always get Vasten 2 in the limit. But it might happen that this norm is actually something which is not even induced by a scalar product. It could be something Finslerian in some sense, so not even Riemannian structure in the limit. You get the equality with Vasten 2, so you get that this norm is equal to the Euclidean one, if and only if you have the isotropy condition, like recovering what happens, what Michael Arreto proved in their first result. Okay, and then I just conclude with the promise picture. And this, what does isotropic condition means? So the first time I saw it, I was a bit puzzled and confused. So this is the algebraic condition. So we say that a partition is isotropic if for every node X, this equality between matrices hold, where n of xy is the normal, between the interfaces, the normal on the interface. And I mean, honestly, maybe you can give me some more insights, but when I saw this equality at the level of the matrices, I didn't really get what this geometric interpretation would be. But you can actually do some draw, especially in some nice setting, and try to understand what does this mean. So if you now evaluate this on some vector field, some vector v, let's say on the sphere, then this condition really means that the measure of this red cube is equal to the sum of these terms. Let's say just focus on which I just obtained by taking v here on the left-hand side. And in fact, those terms have a geometric interpretation. And the geometrical interpretation is that you can construct a sort of dual partition. So for every edge and every vector v, I can construct this rectangular with the direction which is parallel and orthogonal to v. And for every edge, I have one of those rectangular. So for example, I have 1, 2, 3, 4 edges and 4 rectangulars. And of course, if I change v, this dual partition changes. And what this condition really means is that the total sum, the area of this gray area here, so if I sum the volume of these guys, I get exactly twice the area of the cube. And I wasn't sure about this even in this very structural case, but you can convince yourself about just moving the hands a bit that really the total area of these guys is twice as much of the cube by just moving around pieces missing and playing a bit. So if you have isotropy condition, you get the convergence. If you don't have it, you just converge to something which is not Bastian 2. All right, and then I just conclude telling you that there might be some, personally for me, interesting problems to go from this result on, which is we actually wanted to try to understand the distance to then try to study the convergence of the flows, for example. So we know that every time we have a distance, we can try also to look at the gradient flows corresponding and try to study the convergence. And then I would also be very interested to discuss some more random setting, like the one of Nicholas, in a bit more general situation in this picture. All right, and I thank you for your attention.
Thank you very much, Lorenzo. Any questions? Yes, please, Simone.
So, thank you.
It's on.
So for connected to the, to this randomness, but more in the spirit of what Nicholas did. So do you think that, so because in this case, as you said, the interaction is very local, right?
Right, yes, it's true.
So if you replace it by a non-local, which still is going to 0, you expect that you still you will recover W2 as soon as you are just a bit non-local, so you have infinite degree, or there is a scaling it between, which might depend on the geometry or something like that.
Okay, that's very interesting. I mean, of course, depends what we mean with non-local, in the sense that, I mean, of course, I'm not completely sure, but the number of connecting edges and being local might be different, right? Because I can just have a very, very dense graph and still have a sort of bounded range of connectivity.
I was thinking precisely your graph,
right?
But instead of being connected just to the neighbors, being connecting also to, so enlarging a bit the radius.
You mean for the final volume or in general? Because in general, it is not only nearest neighbors. So I mean, if you go here, I mean, I draw a picture like this, but in fact, this just for simplicity, I'm completely allowed in our result to get a connection from this guy to verify 1. But the degree is always fixed because it's periodic. I agree. Yes.
If you enlarge.
All right. I don't know. I think might be still playing some role, this problem of the lack of symmetry. Yeah, I still have the feeling that the symmetry of the problem could still be a problem in some sense, but yeah, it's very interesting.
Thank you, Lorenzo. Nice talk. I'm also a little bit confused about the isotropic condition.
Yeah, me too.
So I was trying to understand whether one could reformulate this condition at the level of the equation.
Which equation?
So the continuity equation there.
Oh, right.
So because what does isotropic means? Means that so basically the flow does not depend on the direction, more or less, right?
Yeah, well, it should really mean somehow that there's some privileged directions you should take.
Right.
Okay, that's whatever, because this is really independence of V. This means that this situation happens. So even if you rotate the problem,
it could be that someone, I don't know, for instance, taking like some momentum radially symmetric, and whatever this means.
Well, I mean, I
I
don't
don't know
I
whether.
think, well, that you can see here. So I don't know. In gen, if you ignore the condition,
Mhm, mhm.
you get this, whatever this is actually, because it's not explicit, but it's a norm. And then I think it's really about choosing the let's say the cheapest direction. But I can't really say much more explicit than this when you don't have the symmetry. Yeah, but it's very, very strange in some sense.
You know, it was just an act.
Yeah, no, I get it. Yeah, I will think about it. Thank you.
Thank you very much. Actually, I was also confused about isotropy. I have some thought, but maybe
Yeah.
we can discuss it afterwards.
Of
So
course,
we'll
it
say-
would be very nice. Yeah.
Thank you very much,
Thank you.
Lorenzo. Our last speaker for the workshop